Hello everyone and welcome to Handmade Hero, where we code a complete game live on stream. We are going to continue with the lighting stuff we were working on yesterday. We need to essentially do two things today. One is we have to decide what we're going to be doing about targeting light sources, and then we have to go ahead and implement something that allows us to target those light sources inside our actual raycasting code. We sort of ended on a note yesterday where I was like, well, this came up, I don't have a plan for it right now, and it's going to be fairly complicated, so I want to wait until we have a full episode, and now is that episode. Let me go ahead and, there we go, load up the code here. If I go to handmadelighting.cpp, which is where this code lives, we can take a look at the part that I'm talking about just to get you acquainted with it in the test casting code here. What we want to do is figure out a solution to this problem right here. So what we were previously doing in the test cast is we were saying, well, if we want to cast towards the light source rather than just casting completely randomly, and I do think we want the ability to cast towards the light source stochastically in the actual caster itself, so this is not academic. This is something that we actually are going to need to do to get our convergence good, to get our lighting to be less flickery. We want the ability to specifically target nearby light sources and gather their values at higher rates than we would just randomly hitting them from picking just arbitrary directions. So if you take a look at what's going on inside the probing, what we want to be able to do here is say, look, for a particular casting location, we want it to tell us with some degree of accuracy what the nearest light sources are. And since we raycast bundles at a time, one thing we may want to do is raycast those as a bundle. I don't know if that's what we want to do. Instead, what we may want to do is just have the closest light source in each direction, and then when we break our bundles into directions, maybe we have 6 directional bundles, for example, for 24 total raycasts, or something like that. Maybe we write over one of each of those with it so that the raycasts have a more coherent traversal. I don't really know, and so I think that's, honestly, the bundles need to be coherent, so I think that might be a more likely way we're going to do that. And so when you think about what's going on there, we need some way of getting like that information. We need something like that. And so the problem is we just at the moment don't really have any way of knowing what that light source would actually be. And we don't really know, we don't really have a plan for getting that information. Now, what I think we probably are going to have to do, because I thought about it a little bit kind of in the back of my brain, as you do after you code something and then you're like, well, I got to do this thing next. Sort of, it's on the, it's off in your peripheral thinking there, right? What I would like to do is I'd like to say that we probably need a separate data structure for this. So we probably want to put our occluders into one thing, and we probably want to put our light sources into a separate thing. Now, the light sources also go into the occluders because we need to like raycast against them. But the directional lookup thing probably needs to be something that's purpose-built. So what I think we want to do is something where we sort of have a data structure whose entire goal is just to figure out when you're casting from a particular location, what are the directional casts that you want to do? Like, what are the light sources, in this case, that you actually want to use? And that's primarily what we're going to be working with, right? And so the problem is we have to figure out some way to build that data structure, and it's unclear like exactly what that data structure would look like, and furthermore, it's unclear how accurate we really need it to be or want it to be, and so on. And in our case, the problem that we're going to face is we need something that sort of splits directional lookups in some way, so we can say, all right, for this location in space, give me the closest light sources like up, down, left, right, north, south, east, west, that sort of thing. And so that we can bundle it with the raycast that we're going to do. And so in order to make that data structure, we would need something that can sort of take the locations of the light sources themselves and break them down into sort of regions that where as you cross region boundaries, you would get different answers so that the splits between the regions correspond to times when the closest light source in a particular direction changes to something else, right? And I don't really know how to do that, right? I don't really know what that thing would look like. And so if I actually go here and sort of draw out what we're actually talking about, let me go ahead and put day 571 in here. So like this is the closest light query, right? So the things that I've seen in the past that sort of have this type of a structure to them are usually, you know, I can't think of very many, but the one that comes to mind is like light cuts, right? And the way light cuts work is they sort of build a hierarchy of light sources that looks a little something like this. So let's suppose that in my system, you know, let's take a very simple case. There's, you know, 7 light sources that get pushed into the system. So, you know, maybe we've got a top-down view of just a simple room, and there's 7 light sources. You know, there's one there, there's one here, there's one here, one here, one here, one here, and one here, right? And then we want to create light cuts out of this. What is a light cut? Well, light cut is essentially building up a spatial model of your light sources by grouping nearby light sources together into a tree. So we start by saying, well, okay, these form the leaves of our tree. So we say, you know, okay, here's 1, 2, 3, 4, 5, 6, 7, and those form the base of our tree. So we have 1, 2, 3, 4, 5, 6, 7, and those are the leaves. And then what we do is say, well, how close are these things together, right? And what we could say is, well, 5 and 6 are pretty close together, right? So those might form sort of this new light source, right? Which I'll give these letters instead of numbers, ones that are not actual light sources. This can be like composite light source A, right? So what we would say is these 2 light sources we can form together, and maybe we treat them as one light source who is like here, actually, right? Like a in-between location or something, and we'll call that light source A, which does not actually exist in the real world, but it's a composite of 2 of the light sources that do exist, right? And then maybe we say, well, 2 and 3 are fairly close together as well, so maybe they form light source B, right? And that's like here, you know? Right? So now we've got another one, and then we have like some other light sources here, and those light sources, you know, kind of can't really form together in any particularly clean way at the moment. You might say that the easiest thing to do would like to be extend this out to contain light source 7 maybe. And again, I'm not sure how we would want to build this tree, but I'm just giving an example. So this is not exactly how it would be done necessarily, but just an example. To form light source C, so maybe A and 7 form light source C here, and then maybe that expands to hold this one, which would be, what is that, light source 4 there. And so C and 4, that forms a new light source, which is D. And then, you know, probably it also grabs this one, so probably these 2 come up together as well. So 1 is probably actually secretly over here, right? And that forms E, and then these 2 merge together to form the final light source F, right? And so what you're doing is you're creating successively less resolute light sources where there's less and less light sources as you go up the tree, right? And then the way this actually ends up working in practice is if you just take a look at how close you are to the bounding region of this light source, you keep splitting the light source down until you get lower and lower into ones that are sufficiently resolute for how close you are to them, right? The reason they call this light cuts is because for any particular person who wants to query them, let's say someone who's like right here, and you want to query them, you may find that, you know, you want light source 5 at full resolution, right? So your light cut wants to include light source 5 as a particular thing. So you know that this is going to be in, right? Which means that you've expanded all the way down here. So that means that, like, you know, 5 and 6, this path through the tree is probably completely expanded, right? But then, you may say, well, 2 and 3 really don't need to be, right? So I never even went down this branch of the tree, right? I just don't even use it at all. And so you may end up with some path that just goes like, okay, this is the entirety of the expansion that I'm going to do, and I'm going to let light source, F, if I had to expand it, B will stand in for 2 and 3 entirely, and I'll just never expand those two. E will get expanded out to 1 and D. D will get expanded out to C and 4. C will get expanded out to this one. And we'll end up with a certain, set of light sources here, right? Now, I don't remember the exact ways of building light cut trees that are efficient or any of these sorts of things, so I'm just kind of saying, like, this is probably not quite how you do it. It seems like you really want something that allows you to be more specific about how these get broken down. But just in general, the idea is we build a tree out of these and we only expand the tree in the places we actually care about, and we leave the tree unexpanded in places that aren't that way, right? And so you could imagine us just merging nearby light sources together in that way. And if we did that, then we could actually cut down on the number of light sources that we were choosing to target. And furthermore, there's probably ways that we can do this such that it does help us with the fact that we need our ray traces to be somewhat coherent in terms of directionality. I'm not sure exactly how I would do that. I have to think about that a little bit. But if you imagine expanding the tree in such a way as to figure out like what's going on in each direction from us, so as we expand those light sources that are like nearby to us or whatever, we would be keeping track of which side of us they were on and just like remembering, sieving them out into 6 different arrays to pick from or something like this, right? So I think that's something we could do. I don't really have a solid handle on it, like I say, but I think that's more or less the way that we would want to approach it. So we have some way of basically just like expanding a separate light tree. So I'm just going to assume that's what we want, right? And I don't know the shape of it or exactly what the routines look like, but that's okay. I just know that we're going to have some kind of a separate thing that's going to be special purpose for this. And so I know that I don't have to care about this get spatial leaf for P thing anymore. Like that we can change to just being one that's specific to light sources, right? And so what I'm going to do is say, let's suppose there's a different tree in here. There's a tree that's something like, like light spatial partition or something like this. I don't know what we're going to call it, but like a lighting node or a light node, something like that. And this light node would have to have something like how it expanded out, right? And if it's like something like a binary tree, maybe it's got 2 indices or something like that, this sort of thing. And then what we would do from there is for each one of these light nodes, in like a binary tree where we expanded or whatever, maybe we just have a bounds for it. So we would just say like, P and radius. So it can basically be just treated the same as our other one. So our, it's basically the same as our other spatial partition. So we look at the lighting box here, right? It's the same as this, but it's going to have different information in it. So instead of, it's going to have the P and the radius, and then it's going to have the emission value or something baked in here. So we can basically just use these, and they kind of expand as they go. And we have like synthetic ones, like I said, that kind of, that keep going. Now we may want to do the exact same thing as we were doing in here. So we may want to have a thing where we just have these light nodes are baked in there. So you push light nodes onto the light node set. I don't know exactly how we want to do this stuff, but something like that. So we would build a tree, and the tree would be sort of separate, and then we would use that tree as something that we would, query. And then we would take the light nodes that we found, and we would just sort those light nodes into which direction they were from us. Basically which one of their when we're looking in the different directions for things, we can then make those rays more coherent by sieving these nodes into the correct location. So something like this, and what I'm going to do now is I'm just going to do like some basic work getting that code started, and then we're going to use that to look up the lighting and just kind of get it working, right? Just get a basic thing working, and then we can worry about turning the crank on that once everything's kind of in place, and we start throwing tons of lights in and it starts slowing down and stuff like that. Then we'll start to worry about, okay, how do we start to optimize this code? Because it's already not very optimal. Like the raycaster is at least 4 wide and doing some good space partition stuff. So, the raycaster is not terrible, but this lighting code is going to be brand new and it doesn't really know what it's doing. And so, that part's going to be slower. All right. So when we actually do our build spatial partition for lighting here, what we want to do now is have a separate pass. You can see the pass sort of starting here. We don't actually want this, this light box target P thing anymore. We're going to get rid of that. And instead what we're going to do is we're going to do this pass over the thing where we say, all right, for each of these, we're going to look at the boxes twice, and we can really do this because it's a separate tree, and we don't really need to know those bounds, probably, I would say. What we could do is we can build the base level of this tree. We can probably build it sort of off the bat. I mean, we could build this the same way we build the other one, I suppose. I'm trying to think of, like, how we want to do this. Because when we actually do this split box here, I feel like we could do the same exact thing, but just for light sources, right? So, I mean, let's... If we did occluder bounds here and we did light bounds as a separate thing, and we imagine in here saying, like, okay, there's an if statement that we'll use... and we'll just sort of take 2 separate sets of bounds. One for things that are lights, because we know that. So for anything that is a light, we include it in these bounds. And for everything that exists at all, we include it in the occluder bounds. So things that you can hit are both light sources and walls. Things that you can treat as a light source for sampling only go in this sort of other box set, right? And so, again, I don't really know what this thing should look like, but presumably we can use a very similar sort of splitting for it or something. Like, presumably we can do a pretty similar set of things. I don't really know. I don't, again, really know exactly how we want this to look. But just in terms of like how far away light sources are, I think that's all we probably need to know. And so what we could sort of do here is we could probably run effectively the same code, like more or less the exact same code. And then we could just go ahead and break it down into a binary tree. Now, I really just don't know exactly how we want to do this. But for now, maybe we say we do it exactly the same way. So if you imagine this split box code operating the same way, and I mean, honestly, we may even be able to make it, now that I'm thinking about it, I wonder if we could just do it with the split boxes themselves. So maybe we just build 2 spatial structures and we don't really care whether they're lights or not. And we just have 2 of them, right? So if you look in here and we say, well, we've got sort of a box table that we're, and lighting boxes here, maybe we just have 2 of those and, we just go ahead and use, we just use 2 of those and we build them symmetrically. And so that when you call this, you just use a different root box, right? So we'd add 1 box here and we'd add another box there and off we would go. So if you imagine what that would look like, I mean, it would just really be something like this, right? And instead of the actual box count and this sort of stuff, we would just need like a separate light count and we would need those things to be added, right? So we would need something like root light box here. And we would put that, I also don't know why root box. Okay, so basically it would look like this, right? So you would basically say root light box index, which would be sort of a separate thing, because here we've got the root box index is something we store elsewhere there. So we would have a root lightbox index, and that would be something that we would build sort of as a separate pass. Again, I don't know if these will have to be expanded to be 32 bits or not, because kind of like we may end up having too many nodes. I don't know. This may want to be 32-bit integers at the end of the day, and we can always expand it if we find that it's too little. But, we want our lighting system solution to run fast, so we're probably going to try and limit the amount of things that get thrown into it either way. But anyway, so if you imagine us doing this stuff here exactly the same way that we were doing it, and then we get the root lighting box by using that root lightbox index. In here, once we actually get those out, we can get the center of the light bounds instead of the occluder bounds. And in here, we can get the radius, right, of that light bounds. And so that allows us to, make this system work for both. So we just use the same building function for each, and the difference is one tree has everything and the other tree only has lights, right? Now, since that needs to know how many lights there are, we end up in a situation where this part here is not quite as simple. We need something that has the actual light count in here, and that's going to start out at 0. And in here, I think what we would do is say we need to count how many of those there are, and each time we actually get one, we would need to load it in here, right? So what we would need to do is make it so that we have, honestly, probably this right here, where we say, okay, we've got the root lightbox index, and we're going to make that be the first box of our set. And so inside this, we assume that each of these will just come after it, right? And so we need a way to add the lights in here as sort of a separate thing. Because these have to be continuous. Oh, well, I guess they don't. Yeah, so, all right. So here's the thing. In the lighting box here, right? So we got the first child index and the child count, right? So when we're actually partitioning these things into children, then what we're actually going to see here, I guess, is those indices that we're looking at here, they go into this box table, which is sort of a doubly indirected table, which honestly is not great. I kind of suspect that that's probably not the best way to do this, but because those are going in there, I guess we don't actually need to do anything particularly fancy there. All that needs to happen is in that box table index, we just need to add a reference to this thing, right? So instead of adding box storage, we can just use box reference and point to the box in question. So like here, where we have the box storage index, we can just say, oh, well, we're just trying to refer to this box, and we just need it to be contiguous so that we can split these indices up, right? We don't even really need to store that information in the actual thing itself. It's just we're going to, and it's a little bit wasteful because they're not contiguous and we're trying to pass them down to a separate thing. We'll see how we do. Anyway, so we've got this root box index here that we're now saying, okay, this thing is a light. We're keeping track of how many of these there are. This doesn't actually have to be here if we don't want it to be here, but I'm going to do it this way anyway, just so we have an idea of where this array starts. And so in here we can say, well, the root light box is this one. This is the number of boxes in question, and I believe this is the offset. So this just needs to be like the one after the root box. Let me just make sure that's true. Oh, no, that's not true. So how do I tell it? Oh, it's just a source array. Okay, that makes sense. So in order to tell it where we're actually looking here, that's still a 0. But when we pass the actual source array, which is this thing, I guess that source array for Scratch A has to be set up with that base pointer being correct. So this would be that, I want to say. I don't really know how Scratch B works. We're going to have to go look at this code. What is that? That's the destination. So I'm not sure how that's supposed to be working there. What's going on? How does this thing do this partition? So it's just writing into the source there, and then the destination gets flipped. I'm not sure yeah, this is some pretty crazy code. So the interesting thing here, right, is you can see that basically those two arrays are just used for the splitting and the writing at the end. And so I want to do a walk through this exactly and make sure it's okay. So when the source count is not greater than 4, so if you have 4 or less children, you do nothing, right? So what that means that what you pass in directly for the source has to kind of be correct. And that's okay because that is what's happening here, right? So effectively what we would want to do is say, all right, here's the root lightbox. And by default, you know, I would assume its children need to be correct because in case you have less than 4 lights going into the system, this would have to be able to fall out correctly, right? And so whatever the child count that goes in would be, the first child index would just be source count source for adding box references there. And so the source, well, okay, no, it's correct. So I guess that just works. We'll see. So I think that if we go through and make that a little clearer, and I clean up that code so that and I know that it's working correctly, that will build us 2 light bounds, one for the root light box and one for the root occluder box, and that's probably fine, and probably most of what we need, right? So if I go in here and we make this sort of union work correctly by changing the spelling so it's not busted, we now have a way to look up light sources. And so now mainly what we're looking for here is we need, oops, why can I not get back to the first thing here? Here we go. Mainly what we need here, root lightbox, that's spelled wrong. Mainly what we need here is just a way of now using this light to figure out which light we're going to cast against. If you look at how we're doing it here, essentially what we're doing is we're only casting against just this one light. And what we can do at the moment is we can just use the root light box as the thing we cast against. And if we only push one light down, then that is what that would be, right? Because it would get the correct values associated with it. The only thing that's not going to happen here is the root lightbox needs to actually be set up properly to have its value be an actual average there. Because if you look at what's going on here, we've got this split box or whatever that's happening. And normally in here where we are doing this splitting, where we actually have more of them, we can actually compute some values here, even though these are not computing those values. We do want to actually compute sort of averaging values here. What we need to do is every time we hit something that would be a container, it needs to sort of get some aggregate values associated with it. This right here is effectively doing sort of the splitting process. And so in here what we're doing is we're saying, look, if we have something where we got a valid split, then we're going to go ahead and assign some information, right? And we do, this this sort of subsplitting. This part here kind of needs to have a way of putting the right bounds in there. So you can see where we compute the bounds, right? You can see here what's happening for each parent box is that when we create those two children, we create the new children with the values that we've tracked. So when we do the split, we know what the left and right sides of the split should have for their center and radius, but we don't fill in any kind of light information for them. And what we do need is we need this ref C value to actually be valid, is the thing, right? And so if something is a light source, we know that this is the emission. If it's not, we know that it's the occlusion value. Those are good pieces of information to have, and we need them, right? So what we need here is we need to be able to say, well, the ref C is going to be, in either of these cases is going to be like the ref CA, right? And the ref C in this case is going to be the ref CB, right? And honestly, we should have been doing that for our occluders anyway, because when you hit one of those occluders, you need it to tell you that information anyway, right? You need to know that this thing is a light or an occluder. You need to know what the color values were of the occluder just as much as you need to know what it is of a light source if you're going to stop your traversal. And so that may have also been why we were having that bug where you were getting black for the bounces on when you got too far away, because we may have just not been aggregating our ref CA values, or ref CB and ref CA values, so we were just getting complete knockout of the lighting source there, right? So that was probably a bug separate from this, and we need to fix it for the lighting. We probably are fixing it for the occluders as well, so that's kind of a nice thing. So here where we decide which one of these we're going to have, we can go ahead and take the color union here. So all I'm going to do is say that we have a ref CA and a ref CB. We're going to sum these values together, and we're going to produce a composite color for this thing that's based on, you know, that value. And so the ref C or ref B in this case are just going to get, the ref CA and the ref CB. I don't know why I had that. I wrote them correctly down here, you can see. Those are just going to get these values summed together. So the ref C is going to tally it up. And in this case, we already have counts. So for each of these, we can also now normalize that. So this here can be multiplied by the inverse. So we can do 1 over the total sum. So the total sum in the A side is count A. We can multiply that by the ref to basically get it back down. This is an average, right? So we're taking the average. So to rescale it back down to the appropriate scale. So ref CA and ref CB in this case can both be automatically normalized down because we know that they've each got a count on them, otherwise we wouldn't have recorded it, right? So I think that gives us all we really need for the splitting there. The only problem is that the initial one, the top level, right, doesn't get the value, and that's an issue. We need the light box, the root box itself needs to know that piece of information in order to figure out, like, you know, what its composite value should be. And so for the particular case of the root, we kind of need a separate summation pass that we don't actually get this way. And so I think what we may want to do here is we may just want to say this thing always has to split. I'm trying to think if there's any other way we could really do this. Because since you have to look at them in order to decide the split, you kind of just want to make sure that that happens in line. Yeah, I don't know. I couldn't really say. I don't really know how this should go. But you can see the problem, like the root box in this case doesn't get a proper value, and we would have to write a completely separate routine that just spun through the children of it to actually produce that composite value, which seems like a real pain in the butt. And so that's kind of annoying, and it would be nice if we didn't have to do it. But on the whole, I guess I can't say... I guess I don't really know how we would get around that. I don't see an obvious way of tightening this code up so that I don't have to write that routine separately, because basically it only actually happens on the split, and we could force it so that it always had to split the first time around. And the only problem there is, like, what if you feed it something that can't be split? Like, you have one light source, period. That can't be split, right? So I do think maybe what we kind of need to do here is just actually bite the bullet and make sure that we, you know, right? I mean, I hate to do it, but I don't know what else to do, right? I mean, I feel like that just has to happen. So it's annoying and stupid, but I don't know, you know, it eludes me, at least at the immediate moment, not having thought about it very much, but it eludes me at the immediate moment how to make that code so that it, you know, it can both be efficient and done in line with a split, and then also kind of have a different pass that lets you do it this way. So yeah, I don't know about that. Anyway, if we want to compute these, right? So in terms of like doing the lookup here where we do a calculate refc, here's the root box in question. What we're going to need here is a way to sort of look up, and I mean, you know, let's use the raycast code as a guide because that's showing exactly how you do the lookup. So you can see here, if we wanted to loop over the children of this thing, we would do it like this. That gives us the child boxes. So for each child, right, we're going to look up the box inside the source index here. And then we're going to take that refc value and sum it up, right? So we know the child count. We can basically say, like, look, if there's no child count, then we don't need to do anything because obviously we can't compute an average of no things. So in the case of there's no lights or no occluders, then just 0 for the ref C is fine because it can't really exist. But in the other case here, so if we did ref C equals the initial value of 0, then for each one of these, and I guess I don't know if we may have to do that sort of separately. In fact, maybe I'll do it this way. Let's do it this way. So we're going to start out assuming 0. We're going to then go ahead and for each box, we'll take the ref C value and we'll, you know, sum them up. And then at the end, we will just normalize exactly the way we were doing it before by taking the root box child count, like so, and turning that into a floating point value that can renormalize. So there we've built our trees and we've properly updated the ref C values, I mean barring bugs anyway. Yeah, and up here we just need to declare those. And so now we're building 2 spatial partitions, one for light sources, one for occluders. And we just now, you know, we haven't really, I don't think we've messed with the code in any particular way. For the, what's the word I'm looking for? I don't think we've messed with the code in any particular way for the occluders, so those should still in theory be working fine. So the only thing we really have to do now is change our get spatial leaf for P function to really be something that does more of a light source query for us. And I think all this wants to do at the moment is just kind of do a query, because normally what we would be doing is actually sort of building an array and then randomly picking from it probably. Right now what we're going to do for get spatial leaf for P is just actually pick out the location here. So when we do get spatial leaf for P, I'm going to call this get light leaf for P. This is not going to have to happen now because now what will happen is when we do get light leaf for P, we can just give us back the light box, and then this can get the information out of that light box. So this can be light box P, and now we can cast against it, right? All right. Sort of tangentially, this also gives us a way to understand area light sources more than we could have before, possibly. There are some downsides to how we're doing it. It's kind of hard to say, but we'll work towards these things as we go. So anyway, now that we've got all of this stuff wrapped up, I'm really just looking, the only problem now is I have to get this function working. And so if we look at get spatial leaf for P, we're sort of going to be doing the same thing, but instead here it's get light leaf for P, right? And so here we're going to be doing the root lightbox index. We're starting with that. We're going to be walking the children to find whatever that index is, and then we're going to return it. If we look at how the result is working now, I do want to return a lighting box. And also in here where we do the light color, we could also make that the ref C, but I'm going to do that in separate steps because we're trying to kind of, this is the test code, we're trying to test that this stuff is working properly. And so now this should give us the light that is sort of closest, I guess, to where we are. Now, I guess I would say we need to update this a little bit, and it actually makes the routine a little simpler too. What we can actually say here is we just want the closest one. We don't want you to have to be inside the light source because that doesn't make any sense. So what we really want to do here, I guess, is say, look, there's a result. We're going to assume it's the root light. While we are inside the volume of this thing, we can divide it down further. So we just say, look, while, or rather, we know that that's got to be true, so we can just do this and say, if this thing has children, I guess, you know what, here's the thing. That's what we really want. So while we haven't expanded down to a single light source, keep going. And in here we would just say, all right, for each one of these things, we just pick whichever one of these is closest, right? And we expand the closest one. So instead of doing a is in rectangle, I think we want like a get distance or like distance to box. And I guess we don't have that. Which is what we want. That's unfortunate. I guess I'll have to write it. But what we effectively want here is a best distance to rectangle. So we want like a closest distance, right? And then what we want to do is loop through the children of this thing. And if there was, we know there's a child count because we won't have descended if there wasn't. And so what we want to do is take the closest distance. For each one of these things, we would say like this distance equals get distance to box, and we would just, do this, right? And we would say if this distance is a better distance, use it. Right? And so this is just the thing that's going to go through and like take the closest box. Whatever the closest box is to us, we will expand it and take, that result. This is not actually, I'm going to put a note here, right? This does not actually guarantee that you're going to get the closest light source. And the reason for that is because you would need to revisit other parts of the tree to ensure that there wasn't something inside a bounding box that was actually closer, even though that bounding box was further away. And the reason for that is, of course, when you create bounding boxes, they're approximations to what's inside them. You don't know if there was actually a light source anywhere near that boundary that you found was closest to you. And so you're just kind of saying, well, this might be something close to me, but it's not necessarily. And so we're not trying in this case to actually find that exact result. And so I just want to make that clear. So in terms of finding the distance to the box, I guess we don't have any functions in our math library for doing that, unfortunately. So that's a little unfortunate, right? But if we wanted to have one, right, and we wanted to say get distance to the box, and we just said center, radius p or whatever. If I wanted to be able to do this, it's actually not that bad. Really, you probably want to do this off of an actual rectangle because you kind of want the min and max, which again, I'm not sure why we may want to change our boxes to storing mins and max instead of p's and radii. And the reason for that is just looking at it, I'm not sure that it seems like we want the min and max way more often than we want the center. And so, I might put that in here as a thing to do. It's just an efficiency concern. When we're all done, I'd like to look at that because, you just want to make sure you're not doing extra math you don't have to do. So we may want to change that, and we'll leave that for later because it's strictly an efficiency concern. It doesn't affect the math in any way. It's just, hey, which one of these things results in less ops to do the same, math that we're trying to do. So we want to make sure that we're not doing extraneous sort of adjustments that don't need to happen because of the way we chose to store it. Now, when we call get distance to box, what we need to do here is say, all right, let's figure out how far away we are from each of these things. I think really this is just a series of mins and maxes. Trying to think if there's anything particularly weird about it. But I think you just need to take the minimum distance from each of the sides of the box, right? I think so. So I think it's just this. I think we just say the test point that we're going to create is going to be I'm actually going to do this. So if I take the box.min, right, and I say, look, what I want you to do is create a fictitious point on the box that is the closest point to us. And what we would do there is say, well, that point, is going to be the minimum of the box and us, right? So whichever of these, the maximum of these two. So whichever one of these is kind of closer there, right? And then the minimum versus the maximum of that. Right? And so if you look at what happens here, we're basically saying, look, if, first of all, take the box's minimum span, the place where the box starts, and us. So if we're further to the left on the number line, if you will, of this thing, we're going to take the box's one. But if we're further to the right, we're going to take us. And then we're going to do the same thing on the other side, but for the maximum value. So if we're less than the maximum value, we're going to keep ourselves. But if we're further, we're going to take that. So this just clips the point effectively to inside the box, right? And what we want to do, we don't have an element minimum, do we? Or a minimum that works on vectors. I don't know if we do. We don't. Well, we sort of do that. We have that one. Well, yeah, but I don't see one for actual vectors. So if you take a look at what this is doing, it's just producing a clipping of our point to the box itself, right? And if we do this for each of our sort of coordinates separately, then what we get is a point that is on or inside the box that is the closest point to us, by definition, right? Because it tried to move to be as close to us as it could be without exceeding the box. At that point, I think we just take the distance and we're done. And I'm going to make this a squared distance because that means we don't take the square root, which in a lot of cases is all we would really need. So why bother taking a square root? You don't need to. Right? And so what I might do is break this into two functions. One is get closest point in box. And so this actually returns us that point, right? So here's the resulting P. And then here where we do the actual closest distance, now I would just say like, oh, okay, so closest, you know, P, that's something we needed to do anyway. Oops, so we might as well have, allow whoever is calling us to get either one so that they can choose whatever they want to do here. So then we can say, well, the closest point, you know, is here, so the distance squared to it is, you know, just the standard length squared call, right? So I think that's all we need, and yeah, I don't see what else we would need there. What is it complaining about? I don't know what it's actually complaining about, to be completely honest with you. What is a rectangle 3 defined to be? Min and max. Cannot convert from real 32 to vector 3. That closes the max, that closes the min, and that's the comma. What is the complaint? Cannot convert argument 1 in max. So there is a max for that? Oh. Okay. Never mind. We do. It's right here. I don't know why I couldn't find it before. I was just looking it up stupid, I guess. So that is exactly what we want. We just want, you know, this is the element min max, right? So, you know, this code now is much easier, right? It's just box max, min, box min, P. Right? So that's all we actually wanted. I didn't know we had one of those, but I guess we do, right? Okay. So now that we have that, that makes it easier to do our queries because now we can just ask those questions about the box. And that sort of makes me curious as well. Like, I'm now wondering, like, do we have a min thing that happens here, but anywhere else? No, we don't. So, yeah. Anyway, that's a typo. Yeah, so it should be the maximum of the min and P, like whichever one is higher, right? And then the minimum of the maximum and that. So, sorry, that was shifted around. All right. So now we just need this thing to actually call that properly. And so since we don't have a min and a max here, again, I think that means we want these boxes to have mins and maxes in them. But yeah, so here's the center half-dim construction of that thing, like so. And again, I think like just that repeated sort of asking what the min and max is just means we probably shouldn't be doing it that way. This is unnecessary now, and I think now we will get the lighting out relatively reliably. We'll see. So this is get distance to box squared, and these are all squared distances because we can compare squared distances and never square root anything in this case. So I think that's what we want. So I think that will do what we need, and now we will be able to get our actual lighting information out when we do get light leaf for P. That'll tell us where the actual light is, and also what its color is, which we can start to test. All right, so a bunch of code spammed out there. Let's get it working, and then we can proceed, I think, with what we need to do. So you can see it's kind of busted, right? You know, just not obviously completely wrong, but also obviously buggy. So now we're going to have to start like figuring out what's going on, right? So the first thing I would like to do is just take a look at what the actual code is returning. So for example, like, you know, in just this part here, I would like to go see, I don't know, is this release mode? Because I probably want to change to debug mode. Yeah. So in debug mode, what I'd like to do is I'd like to take this lighting solution here and say, what are we actually getting back in that routine, right? So, you know, for this, you can see it's debug mode now, so the frame rate's slower. I want to go into the lighting code and just see that what's happening in that test cast. So here's the lighting code here. Let me go to that test. We don't, well, not that test cast, the other test cast. So where is it? Should be right here. There it is. So in this test cast from probes where we're looking over this stuff here, what I'd like to do is just have a thing where I take a look at this and see, because I know what the debug light was actually set to, I'd like to see what this thing tells us, right? So if we look inside the solution, oops, that will have our debug light P in it somewhere. There it is. So we know that like this is what the light is supposed to be at. Like that's where we should get our result if the push happened properly. So let's see what we actually get when we go into this light box thing and what it actually tells us. So when we go here, we're going to see something, right? We've got a child count, which seems good. There's 2 children. I don't know why, because when I think about it, it feels like the number of children should not be that. In fact, as I'm thinking about it, what I really want to do is step into the other part. So I'm assuming there should have only been 1 actual light. So when we or build spatial, this part here, where we do build spatial pressure for lighting, this should have only produced 1 child. And that is not what happened. So I'm wondering if this actual, there you go. So that was wrong. We were passing the number of boxes, not the number of lights. Because I'm like, all right, we shouldn't have seen, you know, that what I just saw was not what we should have seen. So, you know, not good. So now when we step through here, I should see a child count of 1, I'm hoping. Nope, still 2. All right, never mind. Let's go just take a look in there. Let's see what's going on, because I don't know. Maybe we're pushing a lot more lights on there. In fact, you know what I just realized? I guess we are. So because we probably are still pushing on like the lights from the lamps and stuff. So, you know, maybe I should stop doing that for testing purposes. But yeah, okay. So actual light count is 8. So okay, 2 isn't stupid then. That's fine. Let's go ahead and just run this. If I look at get light leaf for P, now child count of 2, well, that's okay, right? No harm done. We're going to look through it here, try to find the closest one, and I'm hoping that the closest one is still actually, you know, let's take a look at what these distance squareds are here, just in case that's also messy. So there's the min and the max. That's quite large. So I guess that's hopefully not a leaf node. I'm not really sure what's going on here. Why are all these so similar? I guess maybe they could be right, but why would you need this many nodes just to divide up 8 lights? This just seems nuts. Something's wrong here. So we got the root lightbox index this way, right? Which I assume is the correct way to do it, but we should probably go check that that's actually correct. I mean, I don't really know, right? So we should probably figure that out. We're going into, and in fact, I guess I could look at the raycast to find out. Yeah, it looks like that's how that works. So we're getting that box out. We're going through the children of it, which I think is correct. So we're iterating over the sources here. And then we're just trying to pick out whatever the next best result is in this case. And I guess the problem is, you know, we want the result to, if we never found something closer, I guess we just want to exit, right? So if the thing we found so far was the closest thing, then we don't want to keep going, but I would assume we want to always expand down till we get to something with no children, although maybe you wouldn't always do that. But I think you would. Like, I don't know how this didn't terminate, like, basically right away. Something's weird there. I'm going to have to go look at the tree construction and find out what's going on. That doesn't really make any sense to me, to be completely honest with you. So we can draw that traversal out, which we probably will have to do. And, you know, we'll probably, you know, have to do it for like 1 point or something like that. But yeah, like, I just don't understand what exactly is happening there with the closest light traversal. That spatial partition doesn't really make any sense to me. I'm not clear on what's going on there, because if you look at what's happening, oh, wait, this also, what is this about? I mean, that doesn't affect anything because we overwrite it, but that shouldn't have been there either. So this should be adding all of the lightbox indexes here so that they, you know, they occur in a row, so that the 8 things that happen after the root lightbox index here, right? I guess this should be a +1, so that it itself is not categorized. Maybe that's what our problem is there, but it seems like there's probably more problems than that. We'll start there. But I'm probably going to have to step through that construction and see what the heck is going on. And I also want to draw it, like, I'd like to take this right here and draw what that spatial walk looks like for some known point. So what I might do is in get spatial, or get lightleaf for P, right? What I should probably do is in here say, okay, for each of these boxes that we get, like, draw the box if this is in the test, right? So we'll do an is test case here, and then like the push debug box, or I don't know, yeah, that. So push debug box should probably go on here, and in this I should say for every single one of these, you know, draw it, right? So I guess we would draw it here, let's say. So maybe this. Like that. I don't know if that's supposed to be a V4. Yeah, it is. And so what we can do here is say, look, we'll push down one test case and we'll draw whatever the result is. What I'll do is, rather than trying to identify what test case we actually want, instead what I'll do is inside testcast from probes, what I'll do is I'll just make a call here where I say, okay, at the start, we'll just take something like maybe the debug light position itself. So we know that, you know, debug light P should always produce itself. Let's do a get lightly for P call where we take and we draw exactly that walk, like so. And so we can see if we're querying the actual point where the light itself exists, what would we actually get, right? And then these we just won't draw because it would produce just a cacophony of cubes and stuff that we don't, you know, would make it hard for us to see what the heck we were looking at, right? And so then we should be able to see how that query works. We'll probably have to turn off lighting because we won't be able to actually see the boxes themselves in that walk without turning off the lighting, but that's easy enough. Again, something I really, this entire time I keep saying I need to make something that turns this off on a hotkey, and I keep not doing it just because I'm in the middle of something else and don't have the time. So anyway, if we turn the lighting off and we look just at what the actual box query produces, so you can see the box query happening over here. You can also see that it's like totally wrong. It's not even including the point we're at ourselves. So to me, that seems to suggest that our box metric is wrong. Like maybe that function I did for like get closest point, for example, is wrong. Because we're drawing the same things that are in the region, so, you know, presumably it would work properly, at least the picking of the bounds. I don't actually know, but let's find out. So if we do get lightly for P here, I mean, there's one other thing that could be wrong, right? The other thing that could be wrong is we could be picking the correct index, and then when we jump to it, no, we can't, because we're actually pulling them out here. All right, never mind. So I think that means our get distance to box squared has to be wrong, which is fine. And if we look here at it, I feel like this is probably fine, and it's going to be in the get closest point in box part, meaning that when we do get closest point to in box, if we assume that this returned the correct value, it would be pretty hard for this to be wrong because all it's doing is saying, well, the length between these two return that, right? So if we look at get closest point in box here, where we've got the box and the P, like, is that actually producing a reasonable value for the closest point on the box? If we take a look at the maximum of the minimum and the P value that's put in there, you know, again, I guess I should look at these functions and make sure that these functions are operating the way you would expect, but they sure seem to be, right? There doesn't seem to be anything untoward happening there, so that seems fine. So when we're taking the min and the max here, I feel like that should produce the closest point on the box. Let's just verify that by drawing it out, and then we'll see. And then I can also sort of I could draw those points as well, just to see whether we're finding them correctly, which is another thing I can do. But anyway, so if we imagine, so each of these things is happening sort of on an axis separately, so I don't think it will matter how many dimensions we use, 1, 2, or 3. So let's just do it in 2, just to double check, since that should give us everything we need. So basically, we're going to pass in some p-value here, right? And that could be inside the box as well. We don't really know it's outside the box. Let me do it like this, so it's completely outside. Then we'll try one that's completely inside. But what we're saying is, well, okay, so let's suppose we look at just the x-axis, right, of this thing. And what we're saying is, okay, there's 3 points involved. Okay, this is the min, this is the max, and here's the p-value. If we look at the p-value itself, what we're going to find is that we take the min and the max of it, right? So we're taking the max of the min and the p. So here's the min and here's the p, which is the maximum value of these two things, right? And so if the p is on this side, let's take another point, which is q, and that's inside the box, right? So in the case of p and the min, we're going to end up with the minimum point, right? In the case of q and the min, we're going to end up with q, because we're taking the maximum. So we're taking the one that's the furthest this way, right? That's what should be happening, right? So in the case of p and the min, we're going to take this. In the case of q and the min, we're going to take this, right? Which is exactly what we would want. And then we're going to shove that through a minimum call for the box max, right? So that's this guy here, right? So the box max, if that is further this way, it's going to be selected. Otherwise, we're just going to keep whatever we had. And in that case, right, so in the p case, we're going to end up picking this point. In the q case, we're going to end up picking this point. That is the closest point on the box in both cases. I don't see a lot wrong with this. That seems pretty good to me, to be completely honest with you. So I'm not really seeing what's going wrong there. So one thing I can do is break this out a little bit more. So let's suppose we go into the get lightly for p call, and instead of doing it this way, I actually did it manually. So I'm actually going to do this, where I ask for the closest point in the box first, like that. And then I take the length squared myself. So this should not in any way change. Like, this routine should behave exactly the same way as it was behaving. All I'm going to do is actually take the length squared myself in this routine. And now we should get no difference, right? So the diagram that I see now that pops up with the boxes on the side of the map there should be exactly the same, and it is, right? That's exactly what we saw the first time. No worries, right? And so if I then say, well, okay, now show me the actual line here, what I should be able to do is say, if this is a test case, right, I should be able to ask for each box that I was testing, and maybe we push this in there, which one of these actually turns out to be closest. So if I draw like the closest one, the one we end up picking in yellow, and I draw the test cases, let's say in like, you know, the gray or whatever it is, right? Like that. Then what I should be able to do is actually draw a debug line that tells me where the closest P actually was, or, you know, where we think that was. So this would tell me for each of these which one we thought was best, right? And if it turns out to be closest, then that's, you know, we can actually draw that one as well, right? So we know which one we ended up thinking was the best. So I don't know if this will be clear enough of a clear enough diagram for us to actually look at, but we're going to try it and see. Here's us drawing our thing, you know, our closest, you know, which one is the closest point kind of a thing. And if you look at it, you know, I would say that it seems right on this one anyway. I mean, the biggest thing that I'm noting is just the boxes are all over there. It makes me think that maybe the problem is we're just not adding the light sources somehow, because the closest point query seems pretty good. I don't know what to tell you. I don't see a lot of evidence of this being bad. It looks like it's doing exactly the right thing. So what I would say might be going on there is our thing that actually builds the spatial partition might just not be adding all of the actual lights that need to be added or something like that, or that it's adding them in the wrong way. Like, this is not doing what it needs to do. You know what I'm saying to you? So like, we should probably look and see, like the solution scratch A thing. I feel like maybe I need to go see what the heck that stuff is doing, because it may just not be doing the right stuff. I don't know. Let's go take a look. So if we go to add box reference, what you can see here is us pushing these onto the box table. That is what I would expect. I now need to go look at what the scratch stuff is supposed to do. So if I look at what scratch A is supposed to do, so you can see me like recording this thing into the scratch array, and I guess that right there would be the problem. So, and in fact, this right here, when we do add box reference, the box ref count is the only thing that's added. So again, I think that's actually fine. So add box storage is the only thing that adds more information, right? So this is a problem because this will affect the count that we actually loop through. And so this should probably be this. To avoid this being an issue. And then we probably also in here where we do this stuff and add these references, this is going to have to actually keep up with that. So when we add a box reference, we're going to have to make sure that that actually does something. So it would have to look like this. Right? It's not pretty, but that is probably what would have to happen. And again, we can kind of maybe work on this a little bit and make this code nicer. I kind of want to get it working the way that it's going right now and just see if we can get it into some better shape. So let's try to work with this and get this, keeping everyone happy. So when we actually add this box reference here, we need to put into the scratch array, I think at this location, I would assume anyway, solution plus root light box index, right, +1. I would think this would actually properly seed that array so that when we came down here to do this, it would work. Maybe I'm wrong about that. So I guess another problem here would be, does this overwrite any of that? And I don't really know. I don't think so. But I'm not sure. In the case that there's a light, we pack these indices together by sort of putting them off in their own thing, right? And I guess the scratch array, yeah, is just really there for doing the indices. Does this add box? Yeah, so these just get appended on at the end of it anyway. And for these, we just added an actual new box for each of them so they get their own indices, right? Because when you add box storage, well, actually, no, you don't. So how was this exactly supposed to work? Am I missing something here? When you add the box storage on, you're getting back an index to an actual box, right? But when you add a reference to a box, you're adding on what? What is going on? Because so when you add box storage, it doesn't add an actual reference. It just increments the box count. And that doesn't really make any sense because in that case, did we actually just split these so that we don't expect actual children to be sort of referenced. No, because these are working exactly the same way. What the hey? Is anyone else confused by this, or am I the only person who's like, I don't get it? Because I don't see how this helps us. I don't see how this actually works at all, right? Because when you get out here, you add the box references. Well, okay, so I guess this is the thing that does it for you. You place these things into your temp array, and then you just add the box references here. So I guess that does make sense. All right, I can believe that, right? Sure. So I guess that's fine. And we do that in the scratch buffer, so everyone's fine with that, right? And it should be fine. I guess I don't know whether that use of the scratch buffer in the source array here actually creates a problem for us, though. Looking at what happens here, you can see that they ping pong, right, as they go down. But I'm assuming that that's okay because you never really need to, it's never going to overflow into the area where we wrote these things. I don't think. Of course, maybe that's also wrong. Maybe there should be a scratch C that's just for this. Trying to think of how I want to do this. So what I might want to do is just use a scratch C for this. I think I might do that right now, just to make it easier on us. So I think I might do this, where we just say, look, there's going to be a scratch C. The scratch C is going to have these in there. It's not going to do add box reference. It's just going to remember them in a scratch buffer. We won't do this. We'll put this down here so that it happens at the end, just the same way as everybody else. And then this will just do scratch C, and we will make another scratch buffer. All right, so I'm going to do that, and the main reason for that is nothing to do with anything other than I want to make it easier. This debugging, there's too many index arrays, and I don't like having them sitting around for no apparent reason. Yes, I'm sorry, I changed the size of that structure. I didn't remember the program was running. So I'm just going to do that to make it a little easier on myself. So this way I can, because I'm going to have to debug that routine that builds the indices, and I think I might have been doing it wrong. In fact, yeah, hey, what a surprise. Just doing that fixed it. Because I was like, that looks wrong to me because it's using references in a place where it should have been using hard indexes and vice versa. So now it looks like we're correctly finding the light, right? You can see that I'm always finding that light of mine. And you can see I'm properly testing other locations of light sources. So that seems better. And now maybe we can take the test cast and make it actually do something useful here, right? So let's go ahead and try turning the lighting back on. Now that we think we've got a reasonable light spatial query there, and see what happens, just to give us a sense of like where we are at in the debugging process. So what I'm anticipating seeing right is, relatively straightforward use of this light source, but also like things that are closer to other light sources use them instead, right? So that actually does a pretty good job of actually doing sort of crappy lighting for the world. And you can see that It's not what we want because we still have a lot of things where like something is, there's no secondary lighting and it's kind of crap. It's doing hard shadows and all that stuff. So, it's not what we want, but you can now see that we're getting per pixel lighting actually queried even just with this test cast by it's properly finding like the light source to use for various rooms and crap like this, right? So I think that's better, and I think that we're off to a good start. So now what we need to do is we need to actually move into the second phase where when we're doing our casting, we want to start using real casting there. And like I said, so now we need some way of saying when we're actually doing these casts, what direction are we casting in, and we need to figure out a way how we would insert the light source into those casts as well, right? So all of this stuff kind of has to start coming together. And yeah, in order to do that, I think we're gonna have to start. Let's start by just figuring out how we're gonna read our test sphere. And to do that, I would like to jump over to our Handmade sampling spheres generation program because I think we kind of don't need like this cube side weight stuff anymore. So I think the sample direction part is probably all we actually will need, and we can load in those sample directions. I don't know exactly what we're going to do about shoving the light source stuff in there, but we'll take it one step at a time. And so if I go to the light sampling sphere part of things, actually I guess I want to do it this way. Then what you can see is we have an HHsphere app that we use, that we made, that basically, well, it's not an app, it's just a little program. The app has infected everything. It's just a little command line utility, and what it does is it generates a nicely distributed sample sphere for us. And the only thing it doesn't do yet is clump these things by direction. What we want to do eventually is clump them by direction, so that's a big to-do that we're going to have to do here. But what we can do right off the bat is we don't have the cube side weight nonsense anymore. That's not actually going to have to be in there. So we can delete that and delete the printout for that as well. So all of the stuff for like weights can just go. Oops. All the stuff that had to do with weights it doesn't have to be in here, and that's good because it simplifies the process down for us. So get rid of that, get rid of this, get rid of this. And now our HHsphere app is ready to generate something for us that will presumably not have this in it anymore. Let's kill this buffer and ask for that. So this thing, oops, right? So what we want this thing to do is generate us, well, we want it to generate our sort of test sphere. If we look at how it was called originally, I hope we saved that somewhere. I don't know if we actually did. Let's take a look. Looks like we didn't. But what we need to know there is how many array bundles you want there to be, and how many different spheres you want there to be. And if we look at what we've got in our INL at the moment, which I guess I will have to load again, Handmade code INL, it looks like we were doing 16 spheres and 18 ray bundles per sphere. Now, in terms of how many ray bundles we actually cast, I would say, I don't know, 18 does seem kind of high. To be completely honest, I'm not sure that's necessary, but okay, so let's suppose that was the case, I think what we're going to do is say that the ray bundles per sphere, we're just going to do 16, 18, and I think I know what I want to do after that. So we're going to say that the sphere count is 16, the ray bundle count is 18. The destination INL is obviously the same place, so it's handmade sampling spheres.inl. And off we go. I'm going to kill this buffer. This thing will hopefully do a pretty good job relaxing all of our relaxationable relaxers. As you can see, it is trying that right now. And this is just trying to produce a nicely uniformly distributed sphere. And I don't actually know, am I supposed to terminate this when it's low enough, or does it terminate itself? Because I don't actually really remember. Let me take a look. So it will look for a min separation distance. And it looks like we are not super convinced about that. But. And what's it printing out? The max closest point, min closest point distance, min max separation, last min max separation. All right. And I mean, that number is still going down, so it is still getting better, right? I guess. Which I don't know what that is. So that's just the measure we ended up using, which was not particularly fantastic, I guess, is the min-max separation. So the distance between the minimum to the closest 2 points and the furthest 2 points is what we're using. And I guess that value there is the improvement. And so it is still like improving. It just keeps on improving and improving, right? And if the min-max separation is less than 0.25, so I guess we just assume this will eventually get down there. Do we really need our sphere to be this tightly packed? I guess we do. I have no idea. I mean, who am I to say? It's crazy, like, it does seem to really go down quite low. I probably should have compiled in release mode now that I think about it, because we're actually probably quite slow, because this is all in debug mode. But I don't know that I want to actually stop it now because it's almost there, right? Although I am kind of curious. I want to see how much faster it is. There we go. Oh my god. Yeah, well, release mode's a bit faster. Just a bit. All right. So anyway, that should have given us our INL, right? So, oops. Now we've got one that just doesn't have the weights. So you can see here we've got just our big table. And all this table has on it is the sample direction, right? So if we want to do that, let me see here how we're actually producing this. Yeah, so all we're doing is just taking the pointer there. So looking at this inside Handmade lighting, if we wanted to start sort of doing these raycasts, what I'm going to do is maybe just drop that right into here as a test. So, you know, maybe we start by taking for each light probe, we'll actually just do a raycast the way that we would be doing it inside the normal raycaster. And we'll sum those together, and that will give us the sort of the light result. Well, I guess we can't really do that because we need to start distributing the light So assuming that that's our new lighting sample sphere that just doesn't have the weights involved there. Oh, so maybe I won't start this today. We can now start considering calling the actual real function. And the only thing we don't have now, and we want to start targeting light sources as well, but the only thing we don't have now is in compute light propagation. The only thing we can't do is we can't actually use the voxel irradiance from the previous frame to contribute to this frame. This function doesn't actually do anything, right? And so this function has to be written. And the other thing that has to be written, and I don't know if we actually even sketched it out yet, is that every time we go to initialize the lighting, I think we just clear the voxel. And what we need to do is actually be keeping the voxel around. So what you can see here is when we go to begin lighting computation, and here's the stuff that computes where the voxel is, we don't actually do anything here to try to update the contents of the voxel. So here's what we need to do next weekend. Right here, we need to do a thing that like copies contents of the old voxel to the correct location in the new voxel. And then the other thing we need to do is compute irradiance. And here we just need to run the same basic algorithm as we're running in the pixel shader, to a first approximation. It doesn't have to be exact, but something similar to that to get whatever the irradiance would have been at this point. Using like what we'll do is we'll take the specular bounce part out of it. So we'll just be using basically diffuse transmission for secondary lighting. And so in the case where the thing hits a emitter, it'll just use the emitter, and if it doesn't, it doesn't. So then in the raycast here, where we're doing, this, for example, where we're doing the ray direction for dir to light, right? And then in here, we're picking up the directions on our sampling sphere. What I want to do here is have us do have us find a random light source that we're going to pick out of the light sources that are close to this light probe, right? And again, not totally sure exactly how we would want to do that. But I guess what we'd say is anything that's close enough to expand, we expand and put in an array, and then we randomly pick someone from the array to sample. Would probably be how I would do it. Just what I'm kind of vaguely guessing. So, we've got the sample point entropy here that we're using. And so, we do something like use that sample point entropy, like this basically, to randomly pull from a light source or something. So instead of doing direction to light like this, instead what we would do is we would pick 4 random points on the light source, since these light sources are area light sources or whatever, and we'd cast towards that, right? And so in here we would say, well, all right, let's build an array of the n closest lights to us or something. So if you imagined here, you had like, n closest lights or whatever, and I don't know how many there would exactly be, but there would be some, and we would have a find closest lights, and we would do this sort of thing, right? And then coming out of this, we would say, okay, let's pick one of those, and I guess actually we need these to be the actual boxes, right? So these probably need to be like something more like that, right? And then what we would do is say, all right, so coming out of that, we've got the n closest lights, and what we now need to do is pick a random one. So we would say n closest lights, and we would take, something like this. right? So pick a random one of the lights out of here to do the, the starting sort of sample. And maybe we need this thing to be slightly different, right? We may not want it to be based on the same thing that's picking these directional samples for some obvious reasons, because that may affect, like, maybe we want that. So that they're just jittered separately. In here we would say, okay, we pick out one of those, for our bias towards light. And then what we would do is pick some random points on that light source. So, we probably wouldn't want to do this exactly, although right now we maybe will. But in the future, we'll want to like pick random points inside the actual light volume itself. And so then what we will do is bias towards those. So we will, for now we could pick it where we do bias towards light. Here's the, the position, and then off we go. But in the future, what we do is we'd pick 4 actual points on there. And I don't know if we have any functions for doing that, but that's what we would do. We can expand this out a little bit and say that, well, the ray direction, I also don't know if this needs to be normalized, to be completely honest. I'm not sure why it would have to be. I don't know that there's anything in here that actually cares about that. I really don't know that there is. This inversion, I would think, would take care of any non-normalized aspect of the t value. So I want to say that you probably just don't even care. I mean, I don't know. We'll have to double check that, because when we wrote that routine, I don't remember whether we needed to or not. But that inversion should presumably just take care of it. So I think what you could really do here is actually just do like a point on light, right? And then the ray direction would actually just loft up the light probe P, which we already have, so this thing here. We could really do the ray direction is just the point on light minus the ray origin, right? And that would give us the initial ray direction biased towards the light source, and off you would go. So in order to get this working, what we would need, and this is also a to-do here, like this needs to sample 1 extra, right? So really what has to happen here, and this is kind of nuts, is this maybe needs to do that. I guess. Well, even that won't really work, because we need it to update it at the end. And the point is, like, when this thing updates, it's not gonna do the last one, right? And that's the problem. So I don't know exactly how we want this thing to play out, but we have a problem there where we would be sampling off the wrong part of the buffer, right? So we need there to be like an extra, we need there to be like padding in here, if that makes sense. So like to do, add padding and increase by 1 to account for the extra slot used by the light bias. So that would all just work, but we need to kind of just add some padding there, otherwise we'll fetch off the end of this array, which we don't want to do. Who knows what that will do, right? So in here, when we do point on light, for now we can do this as actually that, but in the future we can pick some different random points in that light volume, and obviously I think that would be better. So really what we'll end up with is this, where find closest lights needs to actually do something. Yeah. And I think that's basically it. So we'll leave it there, and next weekend what we'll have to do is actually push through this part of it, which is mostly, I don't think there's going to be that much debugging of this stuff because I think we've already spent a fair bit of time debugging this stuff now. But what we're going to have to spend all our time on next weekend is figuring out how the heck to do updating of our voxel field, right? Because that's the big thing we don't know. This stuff here, spam voxel, we just don't know how we're going to do it, right? And so until we get that straightened away, we're kind of dead in the water. And so that's going to be the thing that we're going to have to then pull onto, and figure out how to do. Let's go ahead and go to the Q&A here. What is the go-to assembler for 64-bit code on Windows these days? Is MASM still maintained, or people moving to NASM? So the answer there, as far as I know, is NASM. So if you want to do assembler, typically it's NASM. So it's this thing. I guess I don't necessarily know why, but I believe the reason is because it's actually been updated to support like generating stuff like PlayStation 4 binaries and stuff like this, or no, that's not the NASM we meant. So I don't actually know. Meow, meow, meow. Like I want to say that some of the rad folks like help with it too. I'm not sure. I don't know how to actually search any of this stuff. Why does Sourceforge even still exist? Is the real question. Yeah, I don't know. My understanding was like that's what people use. I don't really know why necessarily, but I think it's because it's had the most updating. And so, like, if you're going to assemble code with it, you've got the highest chance of it actually producing binaries that can be linked with modern executables. So things that are, have to go through code signing, things that have to pass some kind of a like check, LLVM check that that Sony requires before you ship a PlayStation binary, crap like that, right? And so I don't actually know. I don't actually know if there's any other reason why people use it other than it kind of just got settled on for that, and it's the one that's been the most patched for that. Because, I mean, like, there's also just, like, YASM and stuff, right? And I don't know why, like, you wouldn't use this one and you would use the other one or something. I just don't know. They both, like, for my purposes, like building meow hash and stuff, things like that I wanted to use an assembler for, I didn't notice a huge difference between the two. Like, it just kind of works either way. And so I don't really know, like, I'm guessing, again, that because an assembler is not a particularly crazy thing. So I don't really know exactly where the differences are that matter. I'm going to go ahead and assume that X13 Pixels answered the question about Remedy BG since he is the person who wrote it. Do you think with all recent processor vulnerabilities being found that future processors will use a fundamentally different optimizing architecture? I guess I don't know. I really am not sure. I guess what I would say is my guess would be that in the future, I could see us switching to some kind of thing where we actually had partitioned cores. I could imagine something where, like, you actually just have these, like, security cores that are running, like, code from the web. And then you have, like, actual secure cores insecure cores that are fast or something. I could believe it because I feel like they're going to keep squeezing more and more sort of leakage. Like black hats are going to be able to take advantage of every last little bit of leaky execution. And at some point, what that means is that fundamentally the optimizations you can put into a processor core, either they're always making the chip faster or you can't use them. Because anything that makes a chip faster only in some circumstances is now a security hole for, like, it leaks information, right? Which was going to be exploited by someone at some point. And so I don't know. I do think that there's a possibility that we just won't have symmetric optimizations anymore. And you'll end up with things where it's largely asymmetric, perhaps. So it's like, hey, if you're doing scientific computing and you're the only person on this computer and it's unplugged from the internet anyway, you just run on the fastest possible core setting. Whereas if you're like a data center running like multiple things on one machine, you're going to have to set the dial over to paranoid mode, and all of the cores are slower because they can't actually do any of the actual things that you want. for opportunistic optimization, right? I don't know. What's the go-to thing for learning assembly? No idea. Read the disassembly of your compiler. I mean, would be one big way, right? Godbolt. You know, look at what your compiler's generating, because that kind of teaches you how anything that you know how to type in C, how it comes out as assembly, and so you can kind of get a really quick understanding of what's going on doing that and just playing with it. If assemblers were better, would you consider programming an x86 ARM directly, whichever you're trying to target primarily, for everything? Maybe it would auto-translate on the back end and you could rewrite critical sections for secondary platforms. I mean, the answer is no, because a sufficiently good assembler is a high-level language, right? If the question is, would I like my language to be continuous from assembly up to high-level constructs, the answer is yes, absolutely. It's the primary problem with modern languages is they don't provide a continuous way to refine your program down to manual assembler, right? I mean, that's what all languages always should provide. And so I definitely think that's a good idea, but you wouldn't call that an assembler anymore. I mean, because an assembler is a term specifically used to refer to something that does not do any advanced language constructs, really, right? Macro assembler is about the most advanced thing you're really supposed to be doing before you would have to call it a language, its own language, right? And I mean, to a certain extent, I don't really even know if you can call a macro assembler an assembler. Because at some point, if those macros are powerful enough, they're really constituting a language. And so you really shouldn't call it assembly language, because it's not. It's assembly language plus, at the very least, right? And so I think we're really splitting hairs there if we want to look at it, but I mean, that's my opinion. Any sufficiently advanced assembler is now its own language, which is great, and I'm interested in looking at it. But I wouldn't call it an assembler anymore. It's a new language called whatever you called it, right? Do you know of a write-up similar to How to Avoid C++ Runtime on Windows by Martins Mosaico on the Handmade Hero forum, but for Linux? I don't. I think that would be a good article, but no, I don't. I don't know. All right, that's it for the cues. Let's wrap things up. Close down Remedy. Oops, didn't actually mean to close that, but we'll close that as well. Alrighty, thank you everyone for joining me for an episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along with the series at home, you can always pre-order the game at handmadehero.org, and it comes with all the source code right now, so you can play around with it yourself. Maybe you want to try doing your own averaging of the voxel, and that would probably be a good exercise for the week. It's a tough problem, though. I don't know the answer offhand. We're going to try and figure it out next weekend, but you could give it a shot and see what you come up with. Until then, have fun programming, everyone, and I'll see you on the internet. Take it easy, everybody.